X509. As lucrative as that might be to become the next VeriSign, I don't think that's very much fun or is going to happen. So try to keep things small and decentralized.
That is completely anti-usability to try and reinvent
Yes.
that kind of key sign.
Traffic analysis, I presume you're all familiar with the idea. There's been some pretty interesting research papers within the last few years that you can get a lot of information just by looking at how often people talk and who they talk to. Cutlass is not going for full prevention of traffic analysis. Generally speaking, if I'm talking to Todd, someone will be able to tell.
By
But
default.
yes, by default, it will be blatantly obvious because there will be packets spinning back and forth between us. A feature that's kind of in the hopefully near future but not implemented yet is
protocol spec.
Yes, is tunneling traffic. So I could route traffic to Todd through Kathy, so it would seem as if I was talking to Kathy and Kathy was talking to Todd, or possibly that we were talking through Kathy. And that will be useful both to help, stop traffic analysis a little bit, but more importantly for going over NAT, especially in the case where you've got two users both behind a NAT that they can't modify to forward ports or anything. Chaffing and padding help limit the disclosure from the size of packets and how often they're sent. For example, I think it's 50 packets a second for voice. And so if you're talking and you're seeing 50 packets a second going back and forth in each direction, it's pretty obvious that people are talking. With chaffing and padding, you can basically randomize that to some extent, but as Tarzan, again.
Yeah, exactly.
So, and direct cryptanalysis, which I was actually thinking primarily in the sense of, well, hey, we've got this machine that breaks AES, or something of that nature, but in general, any sort of direct cryptanalytic attack on the cryptanalytic attack on the protocol itself. Replay attacks, IV collisions, which is what screwed up WEP, if I recall correctly, or weaknesses in the actual crypto itself, in the algorithms. As I mentioned, it's a Diffie-Hellman key exchange. All strong algorithms with a hopefully known good implementation. There's no export ciphers, no weak algorithms included for backwards compatibility. The 128-bit initialization vectors mean that the odds of an IV collision are exceedingly small, 1 in 2 to the 64. Well, no. Very small. It's too early to do math. Different keys in each direction, which is actually a pretty important one, that when we first did the protocol, Todd was asking why, and I thought for a second, I can't think of a good reason, but something is telling me, yes, you want this is standard issues thing. And the real problem is, if you're using the same key in each direction, someone can take a packet that you've sent to someone else and turn around and send it back at you, and when you check the authentication code, it will match because it was generated with the same key that you're expecting. This is the provisional 5-year plan for where the crypto is going. I've been kind of constrained into that area at this point. But like I said at the beginning, there was no good UDP-based crypto system. DTLS is working its way through the ITF right now, which is basically TLS 1.1 modified just enough to be usable over UDP. A very common request is support for OpenPGP. People want to reuse their webs of trust, and that is also, actually, I think that may be an RFC now, but for OpenPGP authentication through TLS. So the idea is eventually you will be able to plug your OpenPGP key in, and it will just work with no separate key system. But that will take a while because I code very slowly. Ah, okay, well, if there's any questions about the crypto, in which case I'll hand it back to Todd for internals.
So we're going to talk about, if you did want to help out with the project, we're going to go over the internals of the project. If you guys have no interest in coding and you would like to talk about a different aspect, we can clearly do that. I'm pretty familiar with most of the aspects of the project. But if you're all tired and haven't had enough coffee yet, I'm going into internals. So we have two primary core data structures that run around inside. The one that you'll see passed everywhere is the Cutlass handle. It's the Cutlass T-type. This contains information such as your local private keys. It contains all your local configuration information. It contains the sockets that are open so that it can read across, it selects across all the sockets. It's got a hash table that contains all the connections and mutices protecting that hash table. It's got a hash table containing all your directory entries and mutices protecting those as well. There's a lot of locking. It's a multi-threaded model, which I'm going to get into in a little bit. The other data structure that you're going to see thrown around everywhere is the connection handle. So every connection that you have with a remote person is going to have one of these supporting it. It contains the session keys that you've negotiated with that one particular person, any capabilities that the remote side has. If they've got a unique socket, if you connected to them rather than them connecting to you, it lets you know what socket that is. It's got all the transport buffers, so the state, if you've got channels, multiple channels of data coming in, it's got data for each one of those channels, what gaps you currently have in there. I mean, there's a lot of stuff in here. Actually, each one of these is probably a 30-element struct, and I'm just covering the high points. But that's fundamentally what's in those structures. Now, Cutlass actually internally is a multi-threaded beast. The three core threads are the listener thread, the housekeeping thread, and the user interface thread. Now, the user interface thread is what you yourself would be writing if you were writing to the Cutlass API. The listener thread just sits there and it blocks in a select all day. So it selects across open sockets, waits for packets to come in, and as packets come in appropriately, it'll dispatch them out to wherever they need to go. The housekeeping thread is keeping track of time. So it will sit there and block and sleep. And it will modify, it's actually a use sleep, and it'll modify the use sleep time, and every time it goes through that next sleep, it tries to figure out, well, when's the next event going to be coming up? I'm going to sleep for that long. So things like, by default, if a connection is inactive for 60 seconds, tear it down, get rid of it. If a connection is inactive for 30 seconds, send them a ping. You'd send a ping out, the pong would come back in, the listener thread would come in, lock the connection table, lock that particular connection, update the connection to say it's alive now, and it would go on. The UI thread is what you write, so if you've got actual user input, that needs to go out to the remote side, you would do that, and there are a few API calls that I'm going to cover that you do that through. Now, there are a couple other threads that pop up sometimes, and this is the audio threads. If you've actually got an audio connection or multiple audio connections open, you've got an audio reader and an audio writer thread that are pulling data off the microphone and sending it, and then waiting for packets to come in off the listener thread. They'd get put in the connection's audio buffer. The audio writer thread would wake up, see that it's got audio in the buffer, write it out to the audio device. We're using right now the OSS audio model, which if you've got ALSA support in, ALSA provides OSS handles as well, so you can just use that easily. When we're porting to Windows, that's obviously going to be one of the big things. It's all modular, so it should swap out fairly easily, but that's what we're using for audio right now. We also have these things called action handlers. And action handlers are the way that the listener thread and the housekeeping thread will let the UI thread effectively know that something interesting has happened. Cutlass, as I've mentioned, is currently into a library, and we've got 2 clients right now. And you've got to register an action handling function. So if you wanted to write a client, here's what you would do. You would call Cutlass init. That gives you back a Cutlass handle. Then you'd modify that Cutlass handle, which I'm going to get into. You'd register all of your action handlers, which I'm going to get into. You'd call Cutlass start. Cutlass start actually kicks off all the threads and things run at that point. Now just go handle your user input. If you've got user input, you want to send a file, call Cutlass send file. If you want to send a message, Cutlass send message. And then when you're done, you call Cutlass shut down all. So it's actually a pretty simple flow. You could write a really minimal client in, gosh, probably 100 lines of code in C. It's not hard. Here are some of the highlights of the calls that you would call to modify default values. Most of these are actually optional. So cutlass set port, there's a default that comes out of the handle when you get it initially. Nickname is set to blank string by default. If you want to change your permissions, default permissions are just receive text messages, but if you want to receive files, if you want to receive audio, you'd call the cutlass set permissions. The ones that are not optional down here are the cutlass load private key, which if you've got a key file, it will load it in, and you are supposed to pass a passphrase function, so you get your own passphrase to load private key. If you don't have a private key file, we'd recommend that you call generate RSA key, and that will have that loaded for you. Now, I mentioned the action handlers prior. These are kicked out by the internal threads to you, and they actually are a separate thread that forks off so that the listener thread isn't blocking, waiting for you to deal with that specific action. And they happen on events that the UI might possibly want to know about. So if a user connects to you, an action handler gets kicked off containing data saying, hey, there's this user that has connected to you. If a user offers you a file, if a file transfer is completed. There's a complete list of action handlers that there's probably 25 or 30 of them, and they're all documented in the action handler guide, which is in the docs directory. Now, if there are 25, 30 action handlers and you've got to register them, how do you end up with a 100-line client? Every action handler is optional. You don't have to handle any action. By default, if you don't handle an action, just nothing will happen. It won't kick out an action handler. So if you don't care if a user file transfer has completed, don't register the file complete action handler, and it won't let you know. There won't be any kind of UI message, and that'll be fine. The only action handler thing that is registered by default is the internal message, so things like errors and stuff like that. By default, there's an action handler in there that just prints them out to standard error. If you want to deal with them in a different way, though, you can re-register that action, and that way you don't have to have your messages going out to standard error. You can have them pop up in a little text box, for example. And there's an opaque structure that gets passed to every action handler function that you can extract information. So what connection is this, action associated with? What's the file name? What's the hash of that file? Things like that. I've got pretty much all the useful information that I think you would need in an action handler coming out of there. Read the API docs and see if I'm missing anything, if there's useful information that I haven't actually given you yet. We've also got a test suite that if you're modifying the library, before you send any patches, I would highly recommend that you run the test suite across it first. It does things like check the handshaking, make sure it can talk to itself. It'll send itself, 100 messages ranging from 1 byte to 60,000 bytes. It'll send files back and forth across itself. It won't test its own audio thing. So if you're messing around in the audio subsystem, there is no automated audio tests yet. But if you're making modifications to the library, please run the test suite before you send me patches. It does not also test APIs. There is no API test suite. So if you're making changes to Text Cutlass or GTK Cutlass, you kind of have to just test that on your own. Documentation that we've got, we have a separate /docs directory, and we've got the action handler guide, which is a list of all available action handlers and what information comes what you should be expecting when you register that action handler. It's a pretty consistent API, but sometimes if you get an error action, it may or may not have a remote connection associated with it. So you shouldn't depend on there being remote connection information associated with that error. The API.txt is effectively running you through, except in greater detail, the past 10 slides, telling you, this is the flow that you would need to do in order to write a useful Cutlass client. The goals are just our stated goals, and so if you're ever curious as to think, well, should I make this design decision or not, that would be where you would pull that out of. And these are all open for edits, so if you want to suggest changes, we are open to them. The internals, we've got some locking policies so that we don't end up in a deadlock condition ever, for example. So, for example, thou shalt never lock connections and then go lock the big handle, the Cutlass handle, because everything generally goes lock the Cutlass handle, then lock the connections. So this is those kinds of policies that we've got in there, and it also describes the threads and how they interact with each other. And then we've got the protocol.txt, which